Okay, so hi, my name is Anya Zakor, and our project today is on solid-state batteries, and our historical reference point is the Ford Pinto. For our learning objectives, we will be describing the basic differences between traditional lithium-ion and solid-state batteries, um, and we will be describing the Ford Pinto ethical failure, which is in accordance with ABET number 4 requirement. We will name three unique solid-state or the outcome will be to name three unique solid-state safety risks, propose one safety-focused rule and change in accordance with ABET 2, and discuss why rushing these new technologies can damage the trust in electric vehicles and other technologies.
Thank you. Next, please. Hello, my name is Ryan Connolly. And so the reason this topic is so important is because we're going to be seeing a lot more um, in solid state batteries over the next few decades. And so not only are they going to be important with EVs, but we might also see them in other fields with pacemakers or really anything currently using a battery. So that could be phones, flashlights, a lot of stuff around the house. So it's pretty serious that it's done correctly. And so off to the side, I included an example of what a lithium battery traditionally looks like and what a solid state battery looks like as well. And next, please. Okay. And so, as I mentioned, we're replacing traditional batteries that we've had centuries to get right. And we're potentially rushing something in the next few decades that we're going to be putting in our pockets, in our bodies with pacemakers, and really all around us. And there are currently some issues with this technology. And so this little diagram shows one of them where the lithium anode actually grows needles that can penetrate the separator, short circuiting the battery, which also releases H2 gas during that process. And so this could be pretty dangerous. Thank you. Next, please.
So, a brief overview of solid-state batteries is that they are um, compared to lithium-ion batteries, which are that rely on a liquid electrolyte. Solid-state batteries rely on a solid material, a solid electrolyte, and because they're solid, they're able to be twice as energy dense as lithium-ion. They're also able to charge a lot faster, and in theory, they have a much longer um, uh, longevity to them. They're also marketed as non-flammable because lithium-ion batteries have a problem with thermal runaway. So if they get overheated, they can combust. Versus with solid state, because the electrolytes are stored and the chemicals are stored in a solid medium, they're not as volatile and they're not able to combust. However, as Ryan mentioned, there is the issue of um, the H the gas. There's a couple gases like sulfide gases that they put um, to that get released when the seal is damaged, and that thing can happen when there's these dendrites that form. So the key applications are, of course, to be in electric vehicles because that is sort of the largest format of battery that we currently use in like consumer technology in our society. But even larger than that would be, of course, aircraft, grid storage, and EVTOLs, and maybe other military systems. However, the ubiquity of these batteries would find their way into all consumer electronics such as smartphones, laptops, medical implants, and drones. And so, if there are risks with any of this toxic chemical leakage, which can leak in some very, very short amount of time to deadly levels of toxicity, if there's any issues in that, it could have a very far-reaching effects. So currently, the the it's kind of in pilot production globally, There's like semi-solid hybrid batteries that are entering markets already kind of in this year into next year. There's some in China, some manufacturers in China are coming out with early versions of these. Another challenge there is that it's really hard to make them without defects, and that of course increases the risk, and um, it's harder to predict the behavior of batteries with defects. Um, so yeah, the key barriers are um, dendrite shorts, and yeah, and that they're not currently to the level where they can charge as fast as they would like. Interface delamination, H2S toxicity, and other issues with um, manufacturing them without defects and the cost of that.
Thank you. And so, why is the Ford Pinto important with this? Well, it was a new design coming out by Ford. They were actually aware how dangerous it was, and they decided to go along with it anyway because they figured the lawsuits were going to be cheaper than actually fixing it. And so, when you deal with these cheap cars rushed to market, um, with the gas tank in the rear, accidents occurred frequently, a lot of deaths. And this led to a deep distrust of Ford for a very long time because they didn't take the proper steps to ensure safety. And could this possibly happen with the solid state batteries now if it isn't done correctly? Thank you.
Okay, so as far as the historical lessons from the Ford Pinto, um, Ford was aware of, as Ryan mentioned, of the defect, but chose not to fix it due to their internal cost analysis. And as a result, um, the NHTSA safety standards were enacted, and also they had to undergo criminal liability. And this produced a proactive testing culture because it actually became much more costly to them than they had expected. Um, Currently, when it comes to solid state batteries, there is a regulatory gap because it is an emerging technology. Regulation hasn't caught up yet because there really isn't the research and the knowledge there. So as far as the applicable rules, it's only the generic lithium ion rules, and there's no standards for the solid state battery specific risks, which are quite different than the risks for lithium ion batteries. um yeah, and these the voluntary guidelines that are recommended also lack enforcement because the regulations haven't kept up. So some proposed regulations that we thought about were um, mandatory independent safety testing before market entry, because currently a lot of the safety testing is done by those with a vested interest, which, as we'll see later, can contribute to biases. Public disclosure of known risks and incident reporting. So it's again increasing transparency. So if there is things that go wrong, that increases the level of consent that people can participate in, and also reduces their liability and brings the public in on the full picture. And finally, maintaining criminal liability for concealing defects like the Ford Pinto. It needs to be very expensive to these companies to do something that is life threatening, that is so dangerous, that there needs to be something that makes that so expensive that it overweighs their assumed cost of the lawsuits. Um, so yeah, that is something that has to be, make sure that it has some real consequences. And finally, the impact of these proposed regulations is that it would build trust through transparency. The independent testing would catch risks before the deployment and not after the death. And just, as a the net result of the Pinto disaster is that it created that the regulations for the Pinto actually had a beneficial effect both for Ford and for other car companies, as it really pays in the long term to have a culture of trust, to have people trust your company and your technology, and it pays in the long run to be wise about these kinds of things and to prioritize the ethical framework.
Great, thank you. And so when a company is innovating in whatever field it is, there are some steps that they can take in order to build a positive reputation with consumers. And so one of those real life examples would be with what Tesla did while they were manufacturing and testing the EVs. They would release real test data, even if it wasn't the best, and they would continuously work from it and improve it until it was safe for the roads. And so another one could be offering lifetime warranties specifically for anything that could happen with these solid state batteries. I mean, really having the company have faith in this technology instead of rushing it to market like the Ford Pinto was. And again, just take the time to actually develop it. No rushing when it comes to manufacturing this. Thank you.
All right. So as far as the subject matter experts and biases, um, the subject matter experts are mostly within the industry. So we have industry leaders such as QuantumScape, Toyota, and the Japanese name I don't can't say, Samsung, SDI, CATL, and Solid Power. And these are all EV and consumer electronics manufacturers, as well as some other companies that make things, I believe, for military and stuff. So those are the industry leaders, and then within the academic researchers, there's Dr. Eric Waxman, a an academic who studies ceramics, who founded Ion Storage Systems, Jeff Don, who studies battery degradation, and Yetming Chiang, who who founded A123 Systems, so a founder. Um, the potential biases, they depend on what the where the funding is, where the researchers are coming from or being funded by. So when it's started from corporations, most often the biases come from financial pressure. So the tendency to overstate progress, which actually is something that was very commonly done with Tesla, to kind of build hype and get people on board. And they then would follow that up with transparency in their research and in their data, which is a good, I think, a good balance in a way. But that is definitely a bias that can affect um, startups. Also, yeah, so going along with that, timeline optimism, so aggressive dates, trying to get, fully EV, whatever, by 2030, or however, whatever it happens to be. Um, in the case of consumer electronics, battery technology has really been stalled out for a long time, so is a really big deal to be able to get smaller, more powerful batteries into these devices to really dramatically change the user experience, um, from the current status quo. Within the academic entrepreneurship world, there are often conflicts of interest. So um, research that favors their own company, similar, in cases like Yetming Chiang, like he is a materials researcher, has also founded a company. Um, so there's also a publication bias. So, you know, academic institutions are trying to publish, uh, to gain status within academia, and part of that is coming up with good research and plentiful research. So there's a tendency there to hide failures and to highlight their own successes. So there's a bias there. Next, when it comes to the manufacturers themselves, there is a lot of pressure there, to to again demonstrate their performance. So and also to keep their manufacturing secrets to them, like proprietary, so that they have an edge on other manufacturers. So that causes them to perhaps withhold data. There's also a sunk cost bias. So, when they've invested a lot of money in certain infrastructure to manufacture things in a certain way, even if that's not the best way, they have a tendency to favor that way as much as possible to avoid losing, giving up on that money. And finally, why critical evaluation matters is it prevents accepting corporate claims without scrutiny. So in the case of the Pinto, um, the corporate the Ford was making claims on the safety of the Pinto that were actually exaggerated and did not hold up to reality. Um, and it also distinguishes lab breakthroughs from manufacturing reality. So a big thing is something that's possible to do in a lab. This is not possible to do at scale, and that's kind of currently what's going on with the current state of solid state batteries, because they have they've been able to produce some level of this performance in the lab, but when it comes to the actual manufacturing, it's difficult. And actually, one more thing that we forgot to mention, but when it comes to EVs and like the size of the battery, lithium ion batteries are modular, so there are they'll have like a bunch of little, forget the exact term, but they have a bunch of different little modular pieces. So when you have a really big battery, you have you'll have like maybe 50 of these lithium ion channels, and then when one breaks, you can replace that one. But when it comes to solid state batteries, they are always done as as designed in one big thing. So that means they're much more expensive. And if you have an entire car sized solid state battery fail, you have to replace the entire thing, and at that point the cost might be actually more than the value of the car. So anyway, that's an issue, because then also keeping large batteries like that free from defect is a much more difficult proposition. The critical evaluation also separates safety concerns from marketing hype. So, it's really important to not, as exciting as these technologies can be, it's really important to not get too carried away by that, and to make sure that safety concerns are paramount. And for example, QuantumScape in 2020 claimed that they had essentially a very successful battery with very little degradation over time, but the independent testing showed that it was actually performing about half of that, or even less, even worse.
Great, thank you. And so another aspect of this would be the research and development. And so one important issue whenever some new innovation comes out is, can it be mass produced in a way to make it cheap enough for a lot of people to buy it? And so is this just going to stay science fiction, or is this actually going to become something cheap enough like the transistor became? That was also a solid state. And so another part of it is there hasn't even been enough time to determine the long-term safety of these units in real-life applications, such as with pacemakers and replacing the lithium ion in EVs. And it's been quite a while, and we've yet to really see anything real world come out from this. And so I even attached a little video at the bottom I found on YouTube, which was uploaded in 2024. It sounds like it's been a lot of promises for quite a while, and it's possible that people have started to pick up on this too. Thank you.
All right, yeah. So carrying on for that, in the cultural and generational considerations, on the generational side, you have kind of a resetting of generational memory. So the baby boomers, they lived through the Pinto fires, and this kind of creates a skepticism in them for new technologies, and they are, I mean, obviously not every single individual, but as a group, more likely to be skeptical about and insist on independent safety proof. rather than just trusting companies. Whereas with generations that were not affected by that and did not live through that, such as millennials and Gen Z, perhaps they're more likely to be trusting of new technologies and may accept those claims. And some examples of that being Theranos or the Nikola motor scandals that happened recently. As far as cultural considerations, another big thing is, as a globalized world, it's it's not just about the regulations and the manufacturing culture of the U.S. because we're in a greater manufacturing landscape, where most manufacturing isn't done in the U.S. anyway. So when it comes to the U.S. and the EU, we have a pretty strict regulatory style, although it can be slow to catch up with new technologies. But likely, despite that, and there's a lot of attention faced towards those things, it's likely that that we will have safer solid state batteries here than in other countries. In other countries, especially in a lot of countries in Asia, China, Japan, Korea, different countries, Bangladesh, Pakistan, India, like all these different countries, there is, so in China, Japan, and Korea, there's more of a government industry focus that's very speed focused. Other countries, again, it's very much about a speed and beating out the competition through pure speed and not as much focus on safety or quality. So that would lead to rapid rollout, weaker adversarial checks to what the companies are saying and what the optimism is leading. Yeah, and then in India and Southeast Asian stuff, it's a cost and access thing. So there is a desire to get things out quickly, and also much less of any kind of protections in place there. So most likely, if there's going to be problems so what can often happen is that if there's defects in various things in the U.S. or in other developed countries or Western countries that are not legally able to be sold here, sometimes they're then exported to other parts of the world where they don't have those kinds of protections. And also products from other markets can make their way into the U.S. That's quite common for that, or into other countries again, through black markets or just less regulated channels, and that can again kind of diffuse any kind of, or I should say, permeate any kind of risk that may be going on anywhere in the world.
Great, thank you. And so to wrap it all up, why does the Ford Pinto matter when talking about solid state batteries? Well, firstly, every engineer should know about the Ford Pinto, the lessons to learn from it, not rushing something, not trying to trick consumers, weigh the cost of lawsuits versus um, redesigning. It's important that we make sure we're designing something that'll stay safe. Let's avoid tragedy that can simply be avoided by not rushing it. And let's prioritize ethical decision making when we're innovating. All right. Well, that's that then. Thank you very much.
All right, and our references are a bit combined. There's some references on some of the slides in the presenter notes, and then we have this kind of more generic references here, which are for other slides. So, yep, that is it.